The modern model of the atom. First, we're going to look at light. And this is a new model of the atom. The modern model of the atom begins with the behavior of light. In this picture, we see electrified hydrogen atoms. When those go through a prism, you can see that certain light spectrum are emitted from the hydrogen that is electrified. There's a lot of different waves that we may have heard of. You've probably heard of microwaves, radio waves, all those types of things. So we're going to take some time and cover those for a minute here. So light is a wave. You may have heard of wavelength. As we look at it, it looks like this little upside down Y. That's how you know we're talking about wavelength. This is the distance between identical adjacent points on a wave. You can see the difference here between red light and violet light. Red light has a much longer wavelength of about 700 nanometers, where violet light, sometimes we hear the term ultraviolet light, UV rays, right? They have a much shorter wavelength than the red light of only 400 nanometers. If you look at the chart to the right, it shows all of the different colors that we're familiar with. Red light, 700 nanometers, all the way down to indigo and violet, which are only 400 nanometers. The naked eye is pretty much capable of seeing 380 to 750 nanometers. There is a very wide width of how many wavelengths there are. You can see we go all the way to gamma rays and all the way up to radio and television waves. But a very small portion of that is actually what we're able to see. The 380 to the 750. To calculate the energy of electromagnetic radiation, we have to use this formula. The energy of the electromagnetic radiation equals H, which is Planck's constant, 6.626 times 10 to the negative 34th joules per second, times C, which is the speed of light, 3.0 times 10 to the 8th miles per second, and the wavelength of the electromagnetic radiation. So what is the energy of blue light that has a wavelength of 450 nanometers? Let's use that model we just looked at. It would be Planck's constant of 6.626 times 10 to the negative 34 joules per second times 3.0 times 10 to the 8 miles per second, that speed of light, divided by the wavelength, which is 450 in this case, times 1 times 10 to the negative 9th, which is what you need to add on to that wavelength. If you did the math and canceled out the appropriate units, you'd get 4.42 times 10 to the negative 19th joules. So what does this all mean? Well, each color corresponds to a certain energy. The indigo violet line was 410 nanometers, the blue line 434, green was 486, red is 656.3. All of those were being emitted from hydrogen, but yet others weren't. So let's look at why. Well, it's really important to understand these things because we use spectrophotometry in clinical chemistry. In the sample solution, as you can see in the cuvette over here, this is where we'd have the patient sample and reagent mixed together. We shine a light through a monochromator or prism, which isolates a wavelength, shines it through the sample, and we are given a detection on the other side. So that is one of the practical uses of this. So we do know that the energy of electrons is quantized. Electrons have only specific discrete energies and no other energy is observed. So we look at two types of physics with this: classical physics with large objects and quantum physics, which works very well with very small objects or particles. So let's look at Bohr's theory. Bohr's theory proposed that electrons travel around the nucleus similar to planets orbiting the sun. These orbits could only occur at fixed distances with nothing between them. Electrolytes are attracted to the nucleus because of their charge. Energy must be added to the electron to move away from the nucleus. When the electrons move back to their original positions, energy is released, as shown in this picture below. So here's a better picture of an up close of how electrons move in these orbits. The closer the electrons are to the nucleus, the less energy they possess. The further away, the more energy they possess. So the lowest energy orbit atom is more stable. It's got a stronger attraction. Think of that magnetic field that we talked about. When you take a positive magnet with a negative, they stick together. The further apart you get those two magnets, the harder it is for them to stick together. So you have different energy levels. So Bohr's model stated that electrons can move only from one orbit to another. Electrons will never be found between orbits. So here are the shells. The name of the orbits are in the model, and they're labeled as the principal quantum number n. We have n equals 1, 2, 3, 4, and 5. So that refers to the shell. The higher the number, the further away from the nucleus we're getting. So with electron placement, the electrons are going to repel each other because they are both negative, right? So two electrons aren't going to stick together. Each shell holds a maximum number of electrons. The maximum number is defined by 2 times n squared for each shell, where n is the shell number. So for example, 2n squared is 2 times 1 squared, which is 2 electrons. Number 2 will have 2n squared, which will end up being 8 electrons, and so forth. So that is how you know how many electrons fit in each shell. So Bohr model summarized that the orbit shells get larger as n increases, the energy of the electrons increase with n, and each shell can hold the 2n squared total electrons. Here's an example of lithium. If you look at your periodic table, and hopefully you have that printed next to you with all of my lectures, the atomic number is 3. We've got 3 protons and 3 electrons. We know there's 2 electrons in the first orbital, but there can only be 1 in the third because there's only a total of 3. So we fill each level as we go, and we'll have more examples here. So the periodic nature of the chemical properties, looking at the valence shell, this is the outermost shell of the Bohr model. The number of electrons in a valence shell defines its chemical properties. So here we can see lithium. He's only got 1, but so does sodium, but yet they are different. We have 2 different energy states of atoms. We have ground state. Ground state is the lowest energy level. The electrons are arranged as close to the nucleus as possible in the Bohr model here. In the excited state, or any state higher in energy than ground state, 1 or more electrons travel away from the nucleus in the Bohr model. I like pictures, so here's a picture. All right, so here we have ground state and here we have excited state. You can see the energy required to jump from 4 to 5, level 4 to 5, is far less than going from 1 to 2, due to the fact that it is very close to the nucleus. The further away an electron gets, the less energy it needs to jump to the next level. There's been some updates to the Bohr model. The Bohr model fails when there's more than 1 electron present. The spectra may contain more lines than originally appeared. The existence of these subshells within the principal quantum shell was proposed. So the principal quantum number n tells you the number of subshells in a shell. The n equals 1 shell has 1 subshell, 2 has 2 subshells, and so on, as you can see in this depiction. So S holds 2 electrons, P can hold 6, D can hold 10, and F can hold 14. Energy increases as you move down the list. S is the smallest subshell and has the lowest energy, and F is the largest with the highest energy. So as the number increases, you can see the principal quantum shells appear to move closer. This is an example of what N1 through 4 looks like with their different subshells. The energy of the subshells, some shells can overlap as a result of energy level moving closer the further they are away from the nucleus. 4s has a lower energy than 3d. This explains why potassium has only 1 valence electron. I'm going to take a second and show you the electron configuration of potassium.
To find the electron configuration for potassium, we'll look on the periodic table and find the atomic number. That's the number above the element symbol. It tells us the number of protons, but it also tells us the number of electrons. And once we know the number of electrons, we can write the electron configuration for potassium. We'll use the chart on the right to help us. So we go down the first row and we have 1s. S orbitals can hold up to 2 electrons, so we'll put 2 electrons in that first orbital there. Then we have the 2s in the second row. That can hold 2 electrons. We go to the third row and the first term is 2p. P orbitals can hold up to 6 electrons, so we'll put all 6 electrons in that 2p orbital. We've used a total of 10 electrons so far. We have 19 for potassium. Also in the third row, we have the 3s. We'll put 2 there, and then we'll go to the next row. In the fourth row, we have 3p. We'll put 6 electrons in the 3p. At this point, we've used 18 electrons. We only need one more to get to that 19. So after the 3p in the fourth row, we have that 4s term. And all we need to do is put 1 electron there. 2 plus 2 plus 6 plus 2 plus 6 plus 1 gives us a total of 19 electrons, the number of electrons we have for the potassium atom. So that is the electron configuration for potassium. This is Dr. B, and thanks for watching.
All right, thank you, Dr. B. I really liked that video. I thought that he did a nice job of explaining how to do the electron configuration. And that would explain why potassium has only
Hello,
one.
welcome to today's video.
Oh no.
Today we are going to learn how to draw an electron configuration as well as learn the shorthand of...
Sorry about that. Moving on. All right, so that explains why potassium has only one valence electron. All right, so here's what he just went over, and here's another, idea of this. So make sure that you'd be able to cover up this slide and be able to redo that based on how many can fit in each shell and subshell. So using the periodic table, we can see the order of electron filling. Notice that the S block is 2 elements wide, corresponding to 2 electrons in the S subshell. D and P and F have different numbers corresponding to the number of electrons in the subshell. So using the electron configuration to find an element's location on the periodic table, arsenic has an electron configuration of 4s2, 3d10, 4p3. The valence shell is n equals 4, so it will be found in the 4th period. It has 5 electrons, so it will be found in group 5. So the group number pertains to the number of valence electrons on that element. There are many properties that vary in a periodic repetitive way. We're going to look at a few more, specifically atomic size and ionization energy. When we talk about the size of an atom, it's reported in angstroms, nanometers, or picometers. Very, very small. You can see 1 nanometer is 10 to the negative 9th meters. Even smaller is a picometer. 1 picometer is 10 to the negative 12th meters. We see trends in the atomic radius, and it increases as you move down the group, and the radius decreases as you move from left to right. The trend in size is explained that it increases as you move down the group, as you can see here. It increases the number of principal quantum shells. A decrease in atomic size when you move left to right across a period is shown here, and each element adds a proton and an electron. This increases the positive and negative charges. The increased positive charge pulls the electrons inward, making it a smaller atomic size. Kind of like having that stronger positive and negative magnet. It's going to pull it in. Ionization energy is the energy required to remove the outermost electron from an atom. Moving from left to right, the ionization energy increases across a period. Moving down a family, the ionization energy decreases. Here's another picture showing how that works with the periodic table. You can see going across from left to right, ionization increases and it decreases when we go down. And with size, moving across a period, size decreases. The smaller size increases the attraction between the proton and the outer electrons. Each electron in a valence shell is increasingly attracted by the added protons as you move across the period from left to right. As we move down a group, the size increases, decreasing attraction between the nucleus and valence electrons. If you don't have a strong attraction, it's just going to be bigger. The stronger the attraction, the more, I don't want to say sucked in per se, you're going to be to that nucleus. Those inner electrons partially shield the attractions of valence electrons to the protons in the nucleus. In the larger atoms, the electrons are further from the nucleus, therefore less strongly attracted to the positive nuclear charge. As you can see, the weaker attraction here versus a stronger attraction when they're closer together. So with the chemical behavior of the elements, the alkali metals are group 1A, and hopefully by now you have your periodic table out and you have your groups labeled. Group 1A has a very low ionization energy. It gives up electrons very, very easily. You can see sodium, being on the far left-hand side of the periodic table, loves to give up electrons. The halogens, or group 7A, way over on the right-hand side, have a high ionization energy and would rather gain electrons. So if you look at where sodium is on the periodic table and you look at where chlorine is, you can see that sodium will donate those electrons to the chlorine atoms, as depicted here. Next, we're going to look at the octet rule. Elements react to place 8 electrons in the valence shell. So that's where they want to be. It's a filled s and p orbital. It mimics the noble gas configurations. So here we see the sodium and chloride that we just referred to. Sodium has 1 and chloride has 7. They will combine together to make 8. Okay? Sodium is positively charged and chlorine is negatively charged. What about the bonding of magnesium fluoride? Each magnesium gives up 2 electrons and each fluorine accepts 1 electron. Magnesium plus 2 and fluorine minus 1 ions are formed. We can predict charges by the periodic table group. Knowing the number of valence electrons for an element, one can easily predict what final charge will be. For example, group 1, they lose 1 electron, so they tend to become a cation. Group 2 loses 2, so they tend to become a plus 2 cation. Group 3 loses 3, so they tend to become a plus 3. Group 5 gains 3, so they end up with a negative 3. Group 6 gains 2, so they become negative 2, and group 7 gains 1, and it becomes a negative 1. Predict the chemical formula of the compound that results from the reaction between sodium and oxygen. Pause the computer here, look at your periodic table, and see if you can figure out how many electrons are given between each one. Na2O would be the predicted compound. As you can see, Na has 1 valence electron, oxygen has 6. So it can take on 2, because it can fit those 2 little electrons in its orbital to become, or its outer valence shell, to become a complete 8-octet rule. So here's some surprising results of quantum physics. Tunneling is the ability of an electron to pass through a barrier meant to constrain it. This leads us to the uncertainty principle. We don't know exactly where an electron is or where it's going. The more precisely you measure the current location, the less you'll be able to predict the next location. We can think of this as an electron cloud. In this 95% boundary, 95% probability of finding an electron within this area at a given time. So we really don't know. Be familiar with the electron orbital shapes. Electrons exhibit wave-like motion, giving rise to various shapes. The s orbital goes in a sphere. That's easy to memorize. Sphere starts with an S. P orbital, sometimes known as a dumbbell, and the d orbital, which looks like a clover.